in this video we are going to understand about transformer operations on full load conditions. Now here, as you can see, like transformer will be having a core and primary windings and secondary windings. Now I have drawn a full circuit where I have marked current, primary current I1, secondary current I2. So when you will connect a load, then transformers secondary will start drawing some current. So I have noted, I have given notation to this current is I2, and on the primary side I1 current will flow. Now this R1 indicates primary internal resistance of the primary winding. This X1 represents leakage reactance of primary winding. R2 represents internal resistance of secondary winding, whereas X2 represents leakage reactance of secondary winding. Now here the flux in the core which is required to be maintained is phi m. Now while you connect a load here, at that time some flux phi 2 will get produced, and this flux will oppose the main flux. Now transformer, in order to maintain the constant flux in the core, transformer will draw some extra current from the primary winding, and this current will produce some extra flux phi 1 dash, so that phi 1 dash becomes equal to phi 2, and both will be in opposite direction, so that main flux phi m must be maintained at some constant value. Now considering all those parameters, which is something known as a practical transformer, if we want to draw a phasor diagram, we can draw it like this. Now here there are two currents which I have marked upon, which is working current and magnetizing current. So as we know that from the primary winding voltage, working current will be almost in phase with the voltage, whereas magnetizing current will be in lagging by 90 degree as compared to a voltage. Now if you take a phasor sum of working current and magnetizing current, it will give you a I0 current, which is no load current. Now as we are right now discussing about the transformer on full load condition, now transformer will draw I2 current. Now this I2 current will be lagging as compared to V2 if load is inductive. I2 will be in phase with secondary voltage if load is resistive, and I2 will be leading as compared to a secondary voltage if load is a capacitive. Now here this E1 and E2 are something known as a self-induced EMF. So this produced due to this flux phi m, and this flux ultimately get produced due to this current I1. So if you correlate everything, now current produced due to V1 voltage, and due to this I1 there is a flux, and due to this flux there is a E1. Now this E1 will get produced in a direction so that it will oppose the supply voltage. So considering that V1 and E1 will be 180 degree out of phase, and V1 and E2 also will be 180 degree out of phase. So in that way E1 and E2 both will be in phase, like I have shown here, E1 and E2. Now if it is step up transformer, then E1 would be smaller than E2. Okay, so E2 is something higher than E1, so that it is step up transformer. Now here this E1 and E2, as I told you, like it will be 180 degree out of phase with respect to voltage V1. Okay, now depending on the power factor, there will be some relationship between V1 and E1. So if I mark voltage here V2, now let's say if V2 and I2 both are in phase, it means like here I2 and V2, now both are in phase, it means load is resistive. Now as you know that there will be a drop across R2, which will be I2 R2. So this is that particular drop, and this J I2 X2 is a drop due to leakage reactance x2. Now as J indicates 90 degree, so this drop will be 90 degree as compared to I2 R2. Now if you take phasor sum of this, so this will give you a I2 Z2, and if you sum up V2 and I2 Z2, this will give you E2. Okay, now here in response to I2, there will be a flux phi 2 in the core, and in order to oppose this flux, I1 dash get produced, and I1 dash produced due to additional current, which is, let's say, I1 dash. So this is I1 dash. This I1 dash will be n times of I2. It means whatever transformation ratio is there, multiply with secondary current will gives you I1 dash, means additional current. So this additional current produce this phi 1 dash, so that phi 1 dash becomes equal to phi 2. Now here we are having two current, one is a no load current I0 and other is a I1 dash. Now if you take phasor sum, so I have marked in the schematic by red, so this is I0 and this green one is the I1 dash. Now if you take phasor sum, this will give you I1. So I1 is the sum of, so I1 is sum of I1 dash plus no load current I0. Now here there will be a drop in the primary, which is I1 R1, so that will be in phase, like this I1 and I1 R1 will be parallel line, right? And this J into I1 X1 will be 90 degree as compared to this I1 R1 line. And if you take phasor sum, so this will gives you voltage V1. Okay, so in that way you can understand like the performance of a transformer on a full load condition. Now what will be the power factor on the primary side? So for that we have to find out the angle between V and I. So V1 is somewhere here and I1 is here. So this is the angle between V1 and I1 on primary side, whereas this is V2 and I2. So in the resistive load the power factor will be, on the secondary side it will be 1, but on the primary side, due to in the presence of no load current, power factor is bit lower, but it will get improvised as compared to no load, because in no load condition our angle would be this, so this bigger angle, right? Let's say this is phi 2, so phi 2 is quite bigger than phi 1. So as you increase the load on the transformer, so ultimately your power factor will get improvised on the primary side. So we will discuss this part. If you do not understand exact operation of transformer, so I will explain you in the another video where how exactly phi 2 get produced, how exactly phi 1 get dash is produced, so that phi 2 get cancelled, and what R2 and X2 and R1 and X2 signifies, and how you can build this overall phasor diagram by connecting various pieces of phasors. So thank you very